For the current lecture, we are going to talk about yet another mechanical example. And this example will be devoted to what happens when we put an additional mass and an additional spring to the original mass spring system. So we are interested in the following system: two masses and two springs attached as follows. The top attachment point oscillates up and down with a particular amplitude, and so the oscillation will be u of t, and the two masses are connected via a first spring which is attached to the mass m1, and the second mass is attached with the mass m2 to the mass m1. They are also oscillating. In order to measure their position, we will consider the mass and the position x1 of mass m1 and the position x2 of mass m2. Now, as the oscillation goes on, it transmits some oscillation to the mass m1 and to the mass m2. And we would like to identify the frequency response of the first transfer function h from u to x1 and the second frequency response or transfer function from u to x2. Now, for that purpose, remember that we can operate as if gravity did not exist, because gravity just induces biases in our results. Now, we write the equations of motion assuming that, and we obtain that d dt or m1 d dt of v1, which is the vertical speed of the mass m1, must be equal to u minus x1 times k1, the stiffness of the first spring. We introduce right away the stiffness of the second spring, plus x2 minus x1 times k2. Now, likewise, m2 d dt of v2 is equal to x1 minus x2 times k2. In order to get the transfer function from u to x1 or u to x2, we need to use the Laplace transform to begin with. And we get that m1 x1 double dot is equal to u minus x1 times k1 plus x2 minus x1 times k2. In other terms, we get that s squared times m1 plus k1 plus k2, everything times x1 plus minus k2 x2 expressed in the Laplace domain now must be equal to k1 times u. That's the first equation that we need in order to compute the frequency response of that system. Likewise, we get that S2 or S squared M2 plus K2 times X2 minus K2 times X1 is equal to 0. Now, let's first get the transfer function from u to x1. We therefore eliminate x2 from the second equation, or using the second equation by writing x2 is equal to k2 x1 divided by s squared m2 plus k2, and we place it in the second equation, which gives, so in the first equation rather, okay, plug it into the first equation, we get that s squared m1 plus k1 plus k2 times x1 minus k2 squared divided by s squared m2 plus k2 times x1 is equal to k1 times u. Or in other terms, reducing everything to the same denominator, we obtain that s squared m1 plus k1 plus k2 times s squared m2 plus k2. Oh, I forgot this is a k2 squared. Minus k2 squared divided by s squared m2 plus k2 is equal to k1u. Finally, leading us to s squared m1 plus, sorry, I forgot to put an x1 here. Okay, so finally we obtain that x1 is equal to k1 times s squared m2 plus k2 divided by s squared m1 plus k1 plus k2 times s squared m2 plus k2 minus k2 squared times u. Therefore, this is the transfer function from u to x1. We will analyze some of its details later. Now we can write that with the expression for x2 from this expression that we will copy for the sake of convenience. So since this is x2, we can write that x2 will be equal to k1 k2 times u divided by s squared m1 plus k1 plus k2 times s squared m2 plus k2 minus k squared. So, to conclude, we obtain two transfer functions. The first transfer function and the second transfer function share the same denominator. It is a fourth power of s, and therefore may look a little bit complicated. On the other hand, the first transfer function has a s-dependent numerator, whereas the numerator of the second transfer function from u to x2 doesn't have a dependence on s. It is constant and equal to the product of k1 and k2. So, given this state of matter, we would like to understand what the frequency response looks like. So, what we are going to do is look at the denominator first. This is the most complex element. As a matter of fact, it is not that complex. To understand that, we will expand it as powers of s squared. The first element is s to the fourth, and the coefficients in front of it are going to be m1 plus m2. The second element is s to the second power, s squared, times m1 k2 plus m2 times k1 plus k2. The fourth, or the third element rather, is going to be k1 k2 plus k2 k2 minus k squared. What is that k? What we meant by that k is this guy, which is therefore k2 squared. And therefore, we obtain k1 times k2. What does this mean? Well, what we can do is compute the discriminant of this second order equation to understand the roots of this fourth order polynomial. The discriminant is m1 k2 plus m2 k1 plus k2 squared minus 4 times m1 plus m2 k1 k2. We can simplify this expression by saying that this is equal to m1 squared k2 squared plus m2 squared k1 plus k2 squared plus 2m1 m2 times k2 times k1 plus k2 minus 4m1 plus m2 k1 k2. Very good. Now, the first thing is for me to check that we don't have any abnormal answer. Indeed, I wouldn't want that we create a undesirable situation, for example, where units are not respected. Dimensionality, in other terms, is not respected. So, let's see. My discriminant appears to be correct. However, I do not like the fact that we have a squared up mass here times the product of stiffnesses, and here we just have non-squared up quantities. That immediately rings an alarm bell in my mind. So I am wondering what could have gone wrong, if anything. Let's see. The error I made comes from computing the fourth power of M1 of S, and the question in front of it. It is not M1 plus M2. Instead, it is M1 times M2. These dimensional analyses are definitely really nice to locate easy mistakes. So now that I have changed things a little bit, we recognize that minus 4 times M1, M2, K1, K2 appears here as another quantity, 2M1, M2, K2, K1 plus K2. So I could do the following, right? This is equal to M1 squared, K2 squared, plus M2 squared, K1 plus K2 squared. And then write that this is going to be equal to plus 2 M1, M2 times K2 times K2 minus K1. Very good. Now, the question arises as to whether this quantity is always positive, maybe, or always negative. So for that purpose, we can write that this is equal to M1 K2 plus M2 times K1 minus K2, K2 squared up minus 2M1 M2 times K1 times K2 times K1 minus K2 plus 2 times M1 M2 times K2 times K2 minus K1. So is this of any particular use? I am not quite sure. Unless we say that there is an additional term which is made of plus 2 M2 K1 M2 squared K1 minus K2 squared Want to be more precise, I should put a minus here. And finally, plus m2 squared times k1 plus k2 squared. I am not sure where this takes us, but the hope is to obtain a positive term only. So this becomes m1 k2 plus m2 times k1 minus k2 squared, and then plus all these terms. I am not totally satisfied with what I'm doing. Let me therefore try something else. I really don't like what I've done. So this expression looks so simple. There must be a more elegant way of continuing on with it. This is equal to m1 squared k2 squared plus m2 squared k1 plus k2 squared plus 2m1 m2, and what we're going to say is that we're going to call it k2. Okay, I know what we're going to say. We're going to say k2 times minus k1 minus k2. Good. Plus the terms that we don't have here and that we introduced here. So the k1 minus k2 here, so there will be plus 2m1 m2 k2 squared. Okay, and then the k1 term, which is here, is already present there. So I believe that we now have the proper expression. That is, we have we have more than we have four terms in K2. Okay, so let's check if this works. 2m1 m2 k2 minus k1 minus k2 plus 4m1 m2 k2 times k2 2k2 gives us this. Therefore, this is also equal to, by regrouping this term as the square of a sum, which is m1 k2 plus m2 k1 plus k2, and this is not a plus, I apologize, this is a minus here. K1 plus K2 squared plus 4m1 m2 K2 squared. That is necessarily positive. Therefore, our discriminant delta is always positive. And the two roots corresponding to that are S1 squared will be equal to minus m1 k2. Let's make some room here because we're running out of room. How do we do that? Well, I guess we can simplify this, say that this is delta, and erase everything else. We now select this thing, we move it up, and we are now ready to restart our developments. The first root will be S1 squared is equal to minus M1 K2 plus M2 times K1 plus K2 plus square root of M1 K2 minus M2 K1 plus K2 squared plus 4 M1 M2 K2 squared. The second root, S2 squared, is equal to, so let's rename them x1 and x2. Oh, and I forgot, divided by, we forgot to divide by 2 times the first quotient, so 2 times m1, m2. The second term is like minus m1 k2 plus m2 times k1 plus k2 minus the square root of the same thing divided by 2m1 m2. Very well. So there are a few things we can say about these guys. The first one is that for sure this term here is always negative. Second, we can look into this term and see whether it is in size bigger or smaller than this term. The answer is not immediately obvious. If this guy were bigger than that term, then this would be a positive quantity. If this guy were smaller than that term, then it would be a negative quantity. So for that, let's compare M1, let's compare M1 K2 plus M2 times K1 plus K2 squared, or we compare that with, we'll square later, with that quantity. But since we hate square roots, we're just going to compare this guy squared versus M1 K2 minus M2 times K1 plus k2 squared plus 4m1 m2 k2 squared. And we obtain m1 squared k2 squared plus m2 squared k1 squared plus m2 squared. Let me correct this. We'll just keep k1 plus k2 squared. So k1 plus k2 squared plus 2m1 m2 times k2 times k1 plus k2, and we need to compare that with m1 squared k2 squared minus plus m2 squared k1 plus k2 squared minus 2m1 m2 times k2 k2 times k1 plus k2 plus 4m1 m2 k2 squared. So comparing these two quantities is equivalent to comparing the same quantities where I suppress the identical terms, and I obtain on the left side 2m1 m2 k2 times k1 plus k2, and the right hand side we obtain 2m1 m2 times k2 minus k1, I believe, times k2. So it is clear that this quantity is smaller than that quantity, and therefore this quantity is also always negative. Therefore, what we have is that the quantity, let me make some room here, okay? The quantity in the denominator, which I call D, will be of the kind let me make some room here. So the denominator, which I just call D, is equal to s squared minus x1 times s squared minus x2. And therefore, since x1 and x2 are positive, that corresponds to two resonances. Typical things that happen in functions, transfer functions of the kind 1 over s squared plus s0 squared. Okay? they resonate at the value s is equal to j times x1 to be more precise, j times square root of x1, d goes to 0. Same thing when s is minus j times square root of x1, square root of minus x1. This is also true when s is equal to plus or minus j times square root of minus x2. D also goes to 0. So we're at those frequencies omega 1, omega 2, which are equal to square root of minus x1 and square root of minus x2, we have the transfer functions go to infinity, which is characteristic of resonances. Now, what we see is that x2 doesn't exhibit any other behavior than that. Now, x1 has an interesting term on top, and this term is s squared m2 plus x plus k2. Okay. So what I'm going to do is, after erasing all this thing, I will look at that term, which again is s squared times m2 plus k2. Well, this is sort of an anti-resonant frequency, or mode. What do I mean by that? Well, at the so the roots of this guy are s is equal to, s, yes, is equal to plus or minus j times square root of k2 over m2. And therefore, when omega, the exciting frequency, is exactly equal to square root of k2 over m2, the corresponding frequency response is 0. Okay? Because this term goes to 0. And therefore, we have no response whatsoever. And interestingly, what we will want to prove now is that this area where there's no response, it's named a notch, happens to be at frequencies that are exactly between the frequency coming from x1 and s1 squared and x2, which is s2 squared. Now, for that purpose, I now would like to compare s squared, which I call x, which is equal to minus K2 over M2. I would like to compare this guy with X1 and X2. If none of my calculations are wrong, we should have X1 less than X less than X2. Now you're going to tell me why all this mess? And my response would be because it's good. So what I want to do is first compare X1 and X. Let us do a little more cleanup. Okay. So I repeat, I say X is equal to K2 over M2. Now, more precisely, minus K2 over M2. Now, let us look briefly at what this guy tells us. Well, this guy contains two negative terms already, and then it contains a term which is minus M1 K2 divided by 2 M1 M2. Now, that's not exactly what we need. Indeed, that would give you a K2 over M2, but that would not be sufficient to order this guy with respect to this guy X2. So let's delete that term. The next thing we can try is just take this guy and say, how does this guy compare with this guy? So my take is that X2 is going to be less than X. For that, all I need to show is that minus, let's see, so minus M1 K2 plus M2 times K1 plus K2 minus this big square root is less than minus K2 over M2. Of course, dividing everything by 2 M1 M2. I can simplify this by keeping the square root on one side and the other terms on the other side. I obtain that K2 over M2 minus M1 K2 plus M2 times K1 plus K2 divided by 2 M1 M2 must be less than that big square root of the discriminant. or 2k2 m1 divided by 2 m1 m2 minus m1 k2 minus m2 times k1 plus k2 must be less than square root of delta. Now k2 times m1 simplifies to create this term, and what we get is that we compare k2 times m1 plus m2 with m2 times k1. Okay, and there is no particular property we have here. Again, we compare k2 times m1. So we write k2 times m1 plus m2 plus minus m2 k1 divided by 2 m1 m2. If this guy happens to be less than 0, then we have our deal. Otherwise, we need to look further. But as you will see, we will have, in fact, the following order. Okay. So this transfer function will simplify to m1 times s squared plus, hold on a second. So it will be m1, hold on a second. And we will figure out the details later. But this is m1 m2 times s squared times plus x1, or more precisely minus x1 times s squared minus x2. This term is the same at the bottom, and here becomes k m2 times s squared plus, minus x. The order is as follows. Without pursuing the matter any longer, you will have the following behavior. If I draw the omega axis here, okay, I will first meet square root of minus x2. Then I hit square root of minus x. Then I hit square root of minus x1, and the amplitude will look as follows. Okay. If I put a magnitude here, we will see that the magnitude at low frequencies would be 1. Okay, so the magnitude of the transfer function will be 1. We can see that by letting s go to 0 here. Low frequency, this is k1, k2 divided by k1 plus k2 times k2 minus k2 squared, which is k1, k2. Therefore, at low frequencies, this gain is 1. The same holds true here as we let s go towards 0. Therefore, in both cases, we have this. Now, for the first transfer function, for the second transfer function, which I write in red, we will first encounter a resonant peak at minus k2. And then, past this, we will go down with a negative slope of minus 2. Okay, when everything is represented in radians per decade and stuff like that. Okay, and then we'll have another peak at this frequency, which I move here out of convenience. And then the peak, so this will be a resonant peak as well. Okay, and then it will go to a minus 4 slope afterwards. Now, for the second item, okay, so let me erase these guys for a second. What we will see, and so this is, by the way, exactly what happens when you compute the transfer function corresponding to the product of two simpler transfer functions. In this case, K1, K2 over M1, M2 times 1 over S squared minus X1 times 1 over S squared minus X2. Just like we have seen in the past, okay? What we can do is take it as the logarithmic sum of two independent elements. So let me redo this thing by using the same tools as what we have used so far, but not using our knowledge of these transfer functions. So I distribute things so that, I know the gain will be 0 dB when S is close to 0. So I will, again, I can rewrite this as a way to simplify all this, saying that this will be x1 over S minus x1 times x2 times S minus x2 and to be absolutely exact, it's going minus x1 divided by s squared minus x1 minus x2 s squared minus s2. It is the same expression. And we will write the following. The transfer function or the frequency response of a single one of those we have seen looks like a gain of 0 dB followed by a peak at minus x1 followed by a drop with a minus 2 slope afterwards. If x2 is greater than x1, we'll see a corresponding transfer function look like this. Okay, and it will be the same but shifted to the right. Again, let's say this is x1 and let's say this is x2. The body plot of the product of these things will be what is shown in pink, which will first follow the first transfer function and then be influenced by the second transfer function, because we take the sum of these two. And the presence of a minus 2 slope repeated twice means that here we have a minus 2 slope, but here we have a minus 4 slope. Phase-wise, here's what we should expect. First, the phase of the first transfer function will start at 0 and then abruptly drop to minus 180 degrees. Okay. The second one will do the same but drop abruptly later down to minus 180 degrees. And so what we should see is the sum of the two effects, which is first an abrupt drop of minus 180 degrees, and then a drop, another big drop. Okay, to another minus 180 degrees, resulting into a total drop of 360 degrees. Now, let us see how we may be able to reduce these guys. And now talk about okay, so let's see if we can do this. Okay, that looks good. Okay, so we have reduced this thing. Okay, now let's do this guy. Nah, let's do it again. And let's also reduce it. To make room for that transfer function. Now that transfer function contains the same terms as this one, but has a slightly different term here. In fact, I can write it as something along the lines of, if I add a term here, okay, so a blue term, with plus, or times, sorry, so it will be the same thing, minus x1 divided by s squared minus x1, times minus x2 divided by s squared minus x2. Okay, something along these lines. Maybe slightly different, but something along these lines. Times s squared minus x divided by minus x. That's the additional term we get. What does that do to our transfer function and our frequency response? Well, let me take this, move it down. Let me take this, erase it. Let me take this, make some room. Let me take this, erase it. And let me take all these guys, move them to the left. Up. Okay, so that's one. Now we can take these guys. Oops. Okay, so I'm going to move this guy first, as I said, to here. And then I'm going to take these guys, which corresponds to the second transfer function, the one corresponding to the displacement of x1. And I'm going to plot the corresponding plot. As I said, the beginning of the body plot is very much the same, meaning that we have on the one hand this transfer function, on the other hand that transfer function. Let me repeat them. In red we have this transfer function, which goes down with a -2 slope after going to a resonance. We have the green one, which is still there. Okay, which goes down with a -2 slope. And again, this is x1, this is x2. But the interesting thing is we also have this guy. Now this guy is the inverse of these guys. Therefore, if I were to plot it, it would look like a mirror image of the other two guys. And it would drop at x. So that when you take the sum of all these transfer functions, oh, and by the way, here it goes not to 0, but instead it goes up with a slope of +2. Okay? So as a result, the composite transfer function, which I will show in pink, first espouses the first guy. The second drops to 0, like the second guy did. 0 is -infinity in Log's case. Okay? Then it recovers and sort of, in a way, recovers at a level which is a little bit lower than here, but it recovers with a 0 slope because -2 + 2 is fine. And then it goes through espousing the same guy as this guy and eventually goes down with a -2 slope as well. Therefore, what we see is this composite and interesting shape whereby the gain goes up, then vanishes, then goes up again, then vanishes. The phase does pretty much the same story. In red is the phase of the first term. And that phase will be like this, just like it was before, with a drop to a -180 degrees. the phase for the green term is the same as before. Again, it drops minus 180 degrees at x2. And this one drops 180 degrees at x1. Now, interestingly, we have the additional term, the yellow term, which goes as a mirror image and goes up 180 degrees at x, which is square root, which is k over m2, square root of k over m2, k2 over m2. And so the phase does this internal interesting trick, whereby it first goes down, then goes back up, then goes back down. And so it does this kind of jagged trip down, then up, then horizontal, then back down. And what happens is that the phase never drops below 180 degrees. This is an extremely interesting characteristic, as we will see, or as you will see later. It also shows that at low frequencies, the two transfer functions are in phase. Transfer function from top displacement to first mass, and top displacement to second mass. Therefore, you should expect that at low frequencies, the two masses are going to be in phase. Then they will remain in phase, and they will be also in phase with the excitation. Now, they will drop in phase and be in opposite phase with the excitation when going past the first resonance. But then afterwards, one of the masses will recover, okay? And the two masses will be out of phase again. The first mass remaining now in phase with the excitation, and the other being out of phase with the excitation. And finally, the phase of the second mass will drop another 180 degrees to be now again in phase with the excitation, while the first mass drops phase and will be out of phase with the excitation. So this is a little bit challenging to see, and therefore what I propose is that we go over the course of an experiment that illustrates this point. That you are about to see illustrates the behavior of the frequency response for a two-mass, two-spring system whose theory was developed just a few minutes ago. The system consists of a motor and a first mass and a second mass, all of them related by means of springs, which are elastic bands, and other springs here, elastic bands as well. The length of the elastic bands has been established so that the proper effects can be obtained with this setup. Here is a detail of the excitation mechanism by means of a highly demultiplied motor. The little electric motor here rotates at several thousands of RPMs, but the motion is demultiplied in such a way that both masses can be excited. The first mass appears here. It is attached to the top and to the bottom. To the top to the spring, to the excitation motor, and to the bottom via spring to the bottom mass. The two masses are properly equipped with markers in such a way that they are easier to track. These two masses are two bolts made out of steel, and as you can see, we can replicate and create a range of behaviors. What I'm going to do now is perform a frequency sweep from low to high frequencies, and what we would like to do is track the occurrence of peaks, the first one appearing here, as well as the phase of the system. During this first resonance that you see here, as the amplitude goes, the phase of excitation at all signals remain the same, and the two masses oscillate in a resonance fashion together. Now, as we go past this first resonant frequency, okay, we eventually get into a quieter region where the two masses are now both in a position of phase compared with the excitation input. But at a certain frequency, which is about the frequency x, here's what happens. The first mass keeps oscillating, but the second mass stops moving, which is characteristic of the notch that we see. As far as phases are concerned, we now get into a region where the second mass is in phase with the excitation, and the first mass past this zero excitation, the frequency at which this guy does not oscillate anymore. Okay, this guy now gets in opposite phase compared with goes into phase, with the excitation, while the other is still in opposite phase. Okay, now here it enters the second resonance, which happens at that frequency x2, and in both cases what happens to the phase drops again, for the two masses to be out of phase, but one of them being 180 degrees out of phase and the second one being 360 degrees out of phase. This has not happened yet, as we are still in exactly at the frequency x2. However, as we go past this frequency, this is exactly that happens. Now, because of the camera's imperfections and because the engine is now rotating very fast, it is hard to see these two masses. So this is the end of this demonstration.